Okay, so when you think robot, maybe you picture, I don't know, a factory arm. Or maybe your vacuum cleaner bumping around the living room.
Useful things, yeah, standard stuff.
Right, useful. But now, picture a robot playing ping pong. And, I mean, really playing fast shots, spin, aiming.
Sounds maybe like a gimmick at first glance, doesn't it? A fun little demo.
Exactly, that's what I thought.
Okay.
But here's the twist we found in the sources. This is actually a pretty big deal for robotics. It's not just for show.
Mm-hmm. It's fascinating how a game, something seemingly simple like ping pong, can push the boundaries of what robots can do. It's a serious test bed.
Totally. So for this deep dive, we're going to get into a specific project, this high-speed ping pong robot from engineers at MIT.
Yeah, we've been looking at the research, the articles coming straight out of MIT, including a paper they just presented at a big robotics conference.
Yeah, so our mission here isn't just to say, hey, look, a robot plays ping pong. It's more about what makes this robot so advanced. How well does it actually play?
And, maybe most importantly, what does mastering ping pong actually teach us about building better robots for the real world? You know, versatile robots that can do lots of different useful things.
We want to show you what these sources reveal about this, well, frankly, surprising link between a fast-paced sport and some really cutting-edge engineering, all tailored for you.
Okay, let's unpack this. So, fundamentally, what are we looking at? It's a robotic arm, right? Multi-jointed, lightweight.
Mounted at one end of a ping pong table, holding a paddle, looks sort of like a standard setup in that sense.
Right. But how does it see the ball? That's key.
The sources say they're using a setup with multiple high-speed cameras positioned around the table.
Yeah, and these aren't just passively watching. They're constantly feeding data, tons of it, into a predictive control system.
A system based on what? Physics? Math?
Exactly. It tracks the ball the moment it leaves the opponent's paddle,
Yeah.
calculates its trajectory in real time, where it's going, how fast, the spin.
And it's not just tracking, it's deciding how to hit it back.
Precisely. Based on that prediction, the robot figures out the best way to intercept it and selects a swing, like a topspin loop or a flat drive, maybe a defensive chop.
And it aims. It's not just getting the ball back over the net.
No, it aims. It tries to place the ball where it wants it to go with the right kind of spin. That takes incredible speed and incredibly fine control.
That level of control in such a dynamic, fast game, that's pretty remarkable. How did they actually test its performance? I saw something about launching a lot of balls at it.
Yeah, the sources mentioned a test run, 150 balls fired at it pretty quickly, testing those different swing types.
And the results, how did it do?
Quite well, actually. An 88% success rate in returning those shots across the different styles.
88% is solid.
And the team points out that its strike speed, how fast the paddle actually connects with the ball, is getting up there. It rivals some good human players and, they say, outperforms previous robot systems they've benchmarked against.
Okay, what kind of speeds are we talking? I saw an initial figure.
They started around 11 meters per second. But the sources say after some refinements, they've clocked paddle speeds up to 19 meters per second.
19 meters per second? That's what, about 42 miles per hour? That's moving.
It is. Now, top human pros might hit 21, maybe 25 meters per second, so it's not quite peak human speed yet. But the engineers described it as getting really, really close to that level of athleticism.
Okay, 88% is high, but what about the other 12%? Where does it tend to fail? Does it just whiff sometimes?
That's a fair question.
Yeah.
The sources suggest misses often happen with really extreme speeds or unpredictable spins, stuff that pushes the limits of the current prediction model, or maybe very awkward bounces.
So edge cases, basically.
Pretty much. It shows that even with sophisticated physics models, the real world or the real ping pong table can still throw surprises. Curveballs, you could say.
Okay, so we know what it is and how well it performs, which is clearly impressive. But this gets to the core question, the why. Why use ping pong specifically? What makes this game such a good proving ground for robotics?
Yes. This is really the heart of it, isn't it? One of the engineers, David Nguyen, explained it really well in the material we looked at.
How did he frame it?
He talked about a spectrum of control problems in robotics. So on one end, you have tasks that need very slow, very careful, precise manipulation. Think like threading a needle or picking up a fragile object.
Okay, slow and steady.
Right. Then on the other end of the spectrum, you have highly dynamic stuff like legged locomotion, walking, running, jumping. That's all about constantly reacting to instability, maintaining balance, dealing with unexpected forces.
Right, constant adjustment. So where does ping pong fit?
Smack in the middle. That's the key insight.
How so?
Well, you need that super fine, precise manipulation to angle the paddle just right, impart the correct spin, hit the ball accurately, but you have to do it incredibly fast.
Right. You mentioned maybe 300 milliseconds reaction time.
Yeah, roughly that window between the ball leaving the opponent's side and needing to hit it. So, to master ping pong, a robot has to nail both. Dynamic adaptation reacting instantly to the fast, unpredictable ball,
Right.
and precise control to execute the perfect shot. It forces you to integrate both.
I see. It's like a crucible that forces those two different skill sets together.
Exactly. And that combination is relevant to so many real-world robotic tasks.
It's interesting how this connects to broader goals, doesn't it? It's not just about building the best ping pong robot in isolation.
Right. While other groups, like you mentioned Omron or Google DeepMind, have built impressive ping pong systems, often using pure AI learning, the MIT team, led by Kendrick Cancio, David Nguyen, and Professor Sang-Da Kim, they're explicitly looking at how the techniques they develop here, how those techniques for blending speed and precision could translate to more general-purpose robots.
Like humanoids, robots that aren't just single-task specialists.
Precisely. Robots that could potentially walk, manipulate objects, and react dynamically in complex environments. And that's where the link to their other major project comes in, the MIT humanoid robot.
Ah, yes. The arm itself, it's actually based on an arm from that humanoid project, isn't it?
It is. It's a modified version. The arm was originally designed for the MIT humanoid.
Tell us a bit about that humanoid. What's its purpose?
So the MIT humanoid is this bipedal robot, maybe the size of a small child. It's designed specifically for testing dynamic maneuvers.
Like what kind of maneuvers?
Things like walking on uneven ground, handling pushes, jumping, maybe even complex stuff like backflips eventually. It's really about agility and dynamic interaction.
And the potential applications they envision.
Areas like search and rescue are often mentioned. Places where a robot needs to move through cluttered, unpredictable spaces, maybe interact physically with the environment, things too dangerous for people.
So they took an arm designed for that kind of mobile, dynamic, balance-critical robot.
And adapted it for this very specific, high-speed, high-precision task on a fixed table.
Interesting. Did they have to change the arm much?
The original humanoid arm has 4 joints, or degrees of freedom, ways it can move. For the ping pong setup, they added an extra joint, another degree of freedom, in the wrist.
Why the wrist?
To give the paddle more dexterity, more flexibility in how it can angle itself to meet the ball and apply different spins, more control.
Gotcha. Okay, let's talk nuts and bolts then. How do they actually pull off this speed and precision? We mentioned the cameras.
Right, the high-speed motion capture cameras tracking the ball. Similar tech to what they use in movies for CGI characters. That data is critical.
And that data goes into algorithms.
Optimal control algorithms, yeah. Basically, complex mathematical calculations grounded in physics. These figure out the absolute best or optimal way for the arm to move the path, the speed, the paddle angle to intercept the predicted ball path and execute the intended return shot.
And doing all that calculation plus controlling the arm in milliseconds sounds computationally intense.
It absolutely is, which is why they use, according to the sources, 3 computers working together in parallel, like a specialized processing pipeline.
Okay, break that down. What does each computer do?
So one computer is dedicated just to processing the raw images from the cameras at super high speed, getting the visual data crunched down.
Right. Computer 2.
That one focuses entirely on estimating the ball's state, its exact position, velocity, maybe even spin in real time based on the processed camera data. Constant updates.
And the third one?
The third computer takes that real-time ball state estimation in the plan from the optimal control algorithm and translates it all into concrete, precise commands for the motors in the robot's arm. It tells the joints exactly how to move, millisecond by millisecond.
Wow, so it's the synchronized digital relay team making it happen almost instantly.
That parallel processing is the key to achieving that sub-300 millisecond reaction time.
And they're not stopping there. Right, it's not just about hitting it back anymore.
No, they've already moved beyond just reactive returns. The newer algorithms incorporate aiming, predicting not just how to hit the ball, but where to send it.
So you could tell it, hit it to the back left corner.
Essentially, yes. You can set a target location on the opponent's side of the table, and the robot will calculate the trajectory and swing needed to aim for that spot.
That's starting to sound like a real opponent.
Getting there.
Mm.
Though currently, because the arm is fixed in one place, its reach is limited. It can only cover a sort of crescent-shaped area in front of it.
But they have plans for that, I assume.
Oh, yeah. The sources mention future work involves making the robot mobile, maybe mounting the arm on a gantry system that can slide along the table, or even putting the whole thing on wheels.
That would dramatically increase its reach, wouldn't it? Let it cover the whole table like a human player.
Exactly. It could return a much wider variety of shots then. They also mention the potential for using it as a training tool.
How so?
Imagine programming it to mimic the specific serves or attack patterns of a particular human opponent. Could be incredibly useful for high-level players practicing against certain styles.
Okay, let's tie this back to the bigger picture again. We talked about why ping pong is a good test bed. How do these specific skills, rapid interception, dynamic movement, precision, translate outside the game?
Well, think about the core challenges they're solving. Reacting extremely quickly to unpredictable, fast-moving things. Planning and executing precise movements under immense time pressure.
Right.
Those exact challenges pop up constantly in unstructured real-world environments where we might want robots to operate someday.
Like the search and rescue example.
Perfect example. Imagine a robot in a collapsed building. It might need to instantly react to catch falling debris to protect someone or itself.
Okay, yeah. Dynamic reaction.
Or it might need to very precisely place a structural support in an unstable area, requiring that blend of careful manipulation while potentially being on unstable ground itself.
Or just navigating treacherous terrain quickly.
Exactly.
Yeah.
All these tasks need that same tight integration of dynamic reaction, balance, speed, and precise action that they're refining by pushing the limits in ping pong.
So what does this all mean for you, listening to this?
Well, I think it means that this MIT ping pong robot is way more than just a cool science project.
It's a really potent proving ground, isn't it? For blending speed, accuracy, and real-time thinking in a chaotic environment. Ping pong provides that chaos.
It really does. And it demonstrates clearly how very specific skills honed in a context like this, tracking, intercepting, precise hitting, are fundamental building blocks.
Building blocks for what, ultimately?
For the next generation of more capable, more generalized robots, humanoids or other forms that can actually handle complex dynamic tasks out in the real world, not just in labs or factories.
So keeping an eye on projects like this gives you a real insight into the foundational science and engineering that's paving the way for future robots. Robots that could genuinely help in critical situations, rescue, disaster response, maybe even exploration.
Places where quick, precise, adaptive actions are literally make or break.
Which leaves us with a final thought for you to consider.
If figuring out how to deal with the crazy bounces and spins of a ping pong ball forces robots to master this balance between reacting on the fly and acting with precision, what other really complex, messy, real-world problems that maybe seem uniquely human right now could robots tackle next using these same underlying principles?